Assalamualaikum warahmatullahi wabarakatuh and hi everyone. Welcome to our group discussion. My name is Iskandar Zulkarnaynn and with me today are
KHAYRA, NURINA, WIRDANI.
So, today we are going to talk about our calculus project, but not the calculation. It's more about how we actually talk through the problem. So, our project is about finding the best time for ambulance driver to turn on the siren. It sounds simple, right? But there is actually a lot of thinking involved. Khaira,
Sure.
when you first heard what the project was about, what did you think?
Okay. For me, honestly, my first thought was this doesn't feel like a maths problem. An ambulance, a siren, traffic. It felt more like something from the news. But then I realized that is exactly the point. The problem looks like a real life situation, and your job is to find the maths hidden inside it.
Same here, and what made it feel more real to me was the data we found. According to a 2025 study in the Medical Journal of Malaysia, only 4.76% of cardiac arrest patients in Malaysia survive to reach the hospital. The average time for an ambulance to arrive is 37 minutes, but the recommended time is less than 8 minutes. That's a huge gap, and traffic plays a big part in that.
Right. And when you think about it, for every extra minute without treatment, the patient chance of survival drop. So time is not just a number in this problem. It's the difference between life and death. That's why this project felt meaningful to us. We were not just solving a math question, we were trying to answer something that actually matters in the real world situation.
Okay. And that is what makes this a non-routine problem. It is not the maths is harder than usual. It is that nobody tells you what the maths should look like. So you have to figure out for yourself. In a normal exercise, the equation is already there. So you just need to solve it. Here, you have to decide what should I even be minimizing, what are my variables, and what are the constraints. So all of that thinking happens before you write a single equation.
Okay, and that thinking process, not the calculation, is what this discussion is really about. So let's get into it.
Okay, so when you first read the problem, what the very first thing you should do, Khaira?
Okay. The first thing is you need to slow down and really understand the situation. Before thinking about any formula or equation, you need to picture what is actually happening. For example, there is an ambulance. So it has to travel from one point to another point. So for one point is the road is congested. So it makes the ambulance move slower. The other point is
Clear.
road is clear. So the ambulance is faster. And then there is a siren that can speed things up, but you can only use it for a limited time. If you don't understand all of that clearly first, any model you build later will probably be wrong. So the focus at the start is on understanding, not on calculating.
Why is it risky to jump straight into equations before you fully understand the problem?
Oh, so for you answer your problems, it because your equation are only as good as your understanding. If you misread even one part, like whether the siren time is in minute or hours, your whole model will break. In a non-routine problem, the hardest part is not the calculus. It's deciding what the calculus should represent. If you skip straight to the equation, you might use the right technique on the wrong model and get the answer that means nothing.
So, when you are reading carefully, what details are the most important to notice?
For me, the most important detail was the constraint. The siren can only be used for 5 minutes. That one fact changed everything. Without the constraint, the answer is obvious. Just use the siren the whole time. But because of the constraint, you have to think, when is the best moment to turn it on. Where along the journey does it help the most? Once I saw that constraint clearly, I understood what kind of problems this was. It's an optimization is exactly where calculus is useful.
So once you understanding the situation, how do you decide what to minimize, Khaira?
Okay, first you need to connect the maths back to the real world code. For in an emergency situation, the most important thing is about the time. Every extra minute can cost a life. So even though you could argue for minimizing fuel or noise, the context make it clear, which is time, the most important thing. Making that decision explicitly is important because the thing you choose to minimize is what your entire module is built around. If you change that, you get a completely different problem.
Why is it worth stating that choice clearly instead of just assuming everyone knows?
Because it shows that you understand the problem, not just the math. Anyone can differentiate a function, but choosing the right thing to optimize and justifying it, that's the part that requires real understanding. It also keep you honest. If you write down why you are minimizing time, you are forced to connect your math to the real situation. And that connection is what makes the answer meaningful.
So, what are assumptions that you need to make, and how did you decide if they were okay to use?
We assume the route is a straight line with two clear segments. We assume that the speed on each segment is constant, and we assume the siren covers a fixed distance at a fixed speed. None of those are perfectly true in real life. Real traffic is messy. Speeds go up and down, roads have turns and traffic lights. But a model doesn't need to be perfect. It just needs to capture the most important parts of the situation. Our assumptions keep the key ideas that the congested road is slow and the siren give a bigger benefit there. So even though it's simplified, it still makes sense.
Oh, so does simplifying the situation make the conclusion less reliable, Hera?
Okay, it makes them less precise but not useless. Think of it like a map. A map doesn't show every tree or every building, but it still helps you get from point A to the point B. A mathematical model works the same way. It is a simplified version of reality. As long as you are clear about what you have simplified, the model can still give you useful and meaningful results.
How did you start thinking about what variable to define?
I ask myself, what is the one thing the driver can actually control? The driver cannot change the road, cannot change the speed limits, and cannot make the siren last longer. But the driver can choose when to turn the siren on. That decision, the activation point, that's the variable. Once I saw that, I could ask, how does the total travel time change depending on that decision? And the question become the function.
Oh, why do you need to split the journey into separate parts when building the model?
Because the speed changed at different points in the journey. Before the sirens, one speed. During the siren, a higher speed. After the siren, the clear road speed. Each part has its own speed, so each part takes a different amount of time. If you try to use one expression for the whole journey, you lose that difference, and the model stops being accurate. Splitting it up is what makes the model work.
Oh, so before you differentiate anything, how did you check that your model was probably correct?
Okay, I checked the extreme cases. If you never use the siren, the journey should take the longest. But if you use the siren as early as possible, it should take the shortest route. I tested the function at those two extremes to see if the result matched what I expected. Okay. So when they did, I felt more confident the model was set up correctly. In non-routine problem, these kinds of checking is really important. It is easy to make a small mistake in the setup. That is only shows up much later when the answer doesn't make sense.
Once the function was ready, how do you know that differentiation is the right tool?
Because we are looking for a minimum, we want to find the point where travel time is the lowest. Differentiation tells you how fast function is changing at any point. When the rate change or when the rate of change is zero, the function has reached a turning point, and turning points are where minimums and maximum happen. So it's not that we just randomly pick differentiation. It's the natural tool for finding optimal value of something that change continuously.
Okay, so what does it mean if the derivative never equals to the zero? What does that tell you about the problem?
It means the function is either always going up or always going down. There's no turning point in the middle. So you can find the minimum by setting the derivative to zero. Instead, you have to check the endpoint of the interval. The minimum will be at one of the boundaries. That's actually a really important moment. It's the math telling you something real about the situation, not just spitting it out a number.
So, why does it matter to connect the derivative result back to real situation? Why not just report the answer?
Because a number on its own doesn't tell you what to do. The whole point of this project is to help make a real decision. If the derivative tells you the function is always increasing, that means travel time always gets worse the longer you wait. So I can say that you can use the siren as early as possible. That is something a driver can actually add on. That is the real value of the maths, turning a calculation into clear practical decision.
Where does integration come in? Why is not differentiation enough on its own?
Differentiation find the best decision. Integration help you understand how much that decision actually matters. For example, we use integration to check whether the siren really does cover 5 kilometer, even if the ambulance accelerate gradually. That's why of testing whether our model is realistic. Integration is also useful for measuring total effect over time, like how many other vehicles get affected by congestion. This thing build up over the whole journey, and integration is the right tool for that kind of accumulation.
So how do differentiate and integration work together?
They answer different questions. Differentiation answers what's the best decision, while integration answers why does that decision matter. One give you the one give you the answer, the other give you the evidence to back it up. Together, they make the conclusion much stronger. It's not just one method saying use the siren early. It's multiple approaches, all pointing to the same thing.
So let's talk about something a bit more personal. What was the hardest part of this project for you? Not the maths, but the process.
Okay. For me, the hardest part was the very beginning. When you first read the problem, there's this moment where you think, I don't even know where to start. And that feeling is uncomfortable. You are used to seeing a problem and knowing the method. Here, there's no obvious method. So you have to create the method. What helped me was just writing down what I knew, not trying to solve anything, like just listing the fact. The speed here, the speed there, the siren lasts this long. Once I had everything written down, the structure of the problem slowly started to appear.
Did you ever feel like you were going in the wrong direction? Like you had to stop and start over?
Yes, actually. Early on, I was trying to make the model too complicated. I was thinking about acceleration, about the driver reaction time, about the exact shape of the road. And then I realized none of that is what the problem is asking. The problem is asking about one decision. When to turn on the siren, everything else is just a background noise. So I stripped the model back to the essential. Two road segment. First one is one siren, one variable. And suddenly it become much clearer.
Oh, what about the maths itself? Was there a point where the calculation gave you an unexpected result?
Yes, and it was actually the most important moment in the project. When I differentiate the function and look at the result, I expect to find a turning point somewhere in the middle, a value of x where you get the best travel time. But the derivative had no turning point. It was just a positive constant throughout. My first reaction was I must have made a mistake. So I went back and checked everything. The function, the differentiation, the interval. Everything was correct. And then I understood the result itself is the answer. A function that's always increasing has its minimum at the very start. Use the siren immediately, that's the conclusion. I just had to trust the maths, even when it surprised me.
Oh. So how did working in group help when you were stuck?
It helped a lot actually. When you are stuck on something, it is easy to keep going in circle. You keep trying the same approach and getting the same result. But when you explain the problem to someone else, two things happen. First, explaining it out loud often helps you spot your own mistake. Second, the other person asks a question you hadn't thought of. That is outside perspective was really valuable. A lot of the time, the solution came out of a conversation, not from sitting alone and staring at the page.
I agree. And I think that's one of the things this project taught us. That goes beyond calculus. Knowing when to ask for help is a skill, and being able to explain your thinking clearly is just as important as being able to calculate correctly.
So we have talked a lot about the maths itself. But let's zoom out a bit. How does this kind of thinking apply beyond ambulance?
Okay. It applies to any situation where you have limited resources and you need to decide when or where to use them. Think about delivery drivers. They have a fixed working time and multiple stops. So the question is, which route saves the most time is essentially the same kind of optimization problem. Or think about a hospital managing beds. They have a limited number of beds and they need to decide how to allocate them across different departments. The maths is different, but the thinking is the same. Identify the constraint, model the situation, optimize.
So, the skill we are really learning is not just calculus, it's, it is modeling, right?
Exactly. Calculus is the tool. Modeling is the skill. Modeling means taking a messy, real world situation and turning it into something you can analyze mathematically. It's mean deciding what matters, what doesn't. It's mean making assumption and being transparent about them, and knowing how they affect your conclusion. That skill is useful in engineering, in medicine, in business, in policy making. Anywhere you need to make decision based on limit information.
Okay, coming back to our specific problem. Did the maths result change the way you think about the emergency response, Rina?
Yes, actually, before this project, I thought of ambulance response as just drive fast, get there as quickly as possible. But the project showed me that it's more nuanced than that. It's not just about speed, it's about strategy. When do you use the siren? Which route do you take? How do you balance your limited resources across the whole journey? And the answer to those questions can be found through mathematics. That was genuinely surprising to me.
So, what about the social impact side of things? The effect on other vehicles on the road?
Okay. That part really stood out to me. We started with one ambulance and one patient. But when we extended the analysis, we found that the optimal decision also affect many other drivers. If the ambulance cleared the congested zone faster, fewer vehicles pile up behind it. That means less disruption for everyone on that road. So, the best decision for the patient is also the best decision for the broader road system. It's a race case where the individual optimum and the social optimum are the same. And calculus was the thing that made that visible.
Does that change how you see the value of learning calculus?
Completely. I used to see calculus as something you learn to pass an exam. You memorize the rules, you practice the technique, you get a grade. But this project show me that calculus is actually a way of seeing. It help you see pattern in change. It help you see how one decision ripples out into consequence. It also help you to see the optimal path through a complex situation. That not just a math skill, that's a life skill.
And I think that's why non-routine problems are so valuable as assignment. They force you to make that connection between the abstract technique and the real world application. If you only ever solve textbook exercise, you learn the technique, but you miss the point. So non-routine problem make sure you get the point.
And once you get the point, you start seeing non-routine problems everywhere. In your daily life, in the news, in your future career. You start asking, what is the constraint here? What am I trying to optimize? And how will I model this? That shift in thinking, that's the real outcome of this project.
Let's try something a bit different. What if we change some of the condition in the problem? How would the answer change? For example, what if the siren could be used for longer?
Okay. If the siren could last longer, the problem changed significantly. At some point, the siren would cover the entire congested segment, and then maybe part of the clear route too. In that case, you would have a real interior optimization problem. There would be a trade-off between using the siren on the slow route versus saving some of it for the fast route. The function would have a proper turning point, not just a boundary minimum. So, the longer the siren duration, the more interesting and complex the optimization becomes.
What if the speed difference between the two segments was smaller? Like, what if the congested route was not that much slower?
Oh, that's a very great question. If the speed difference is small, the benefit of using the siren on the congested road is less obvious. In the extreme case where both segments have the same speed, it doesn't matter where you activate the siren at all. The travel time would be the same. In the extreme case where both segments have the same speed, it doesn't matter where you activate the siren at all. The travel time would be the same no matter what. So the answer is very sensitive to that speed difference. The bigger the difference, the clearer the optimal strategy. The smaller the difference, the less it matters. That useful things to know when interpreting the model.
Yep. Therefore, what if the ambulance had to stop at a traffic lights or intersection? How would that affect the model?
It would make the model much more complicated. Traffic lights introduce random delays. Sometimes you wait, sometimes you don't. With a siren, you can clear intersection faster. So, the benefit of the siren is not just about speed anymore. It's also about reducing random waiting time. To model that properly, you need to use probability and statistics. not just calculus.
Oh.
It becomes a much bigger problem. But the core question is the same. When and how do you use your limited resources most effectively?
So, what if there were two ambulances going to the same hospital? Would the optimal strategy be the same for both ambulances?
Not necessary. If one ambulance is ahead of the others, the first one clears the road for the second. So the second ambulance might benefit from a different strategy. This kind of problem, where multiple agents affect each other, is studied in something called game theory and network optimization. It's a whole area of applied multiplication on its own. But the foundation is the same. You start with a clear model, a clear objective, and a clear constraint. And then you use the right mathematical tools to find the best strategy.
I think what this what if question show us is that the problem we solve is really just a starting point. The real world is more complicated. There are more variables, more constraints, and more uncertainty. But the way of thinking we use, model it, optimize it, interpret it, that approach scales up. You can apply it to more complex version of the same problem. That's what makes it valuable.
Exactly. And I think that's a good way to think about what we have learned. We didn't solve the full real world ambulance problem. We solved a simplified version of it. But in doing that, we learn a way of thinking that can be applied to bigger, messier problem. And that's what calculus at its best is for. Okay, so let's wrap up. We have covered a lot of ground today, from a real world context to building the model, to applying calculus, to the challenge we face, to the broader implication, and even some what if question. Let's each share one key lesson, not about the maths, but about what this project really taught us. I will start. The biggest thing I learned is that understanding counts before calculating. The most important work in this project was not the differentiation, it was understanding the situation well enough to know what to do to differentiate it. If you rush into the maths without really understanding the problem, you might get an answer, but it would mean nothing. This project taught me to slow down and think first.
Okay. For me, it is about interpreting results, not just getting them. In most exercise, you get a number and you are done. Here, the math gives us a result and we had to ask what this actually means for the driver. That step, connecting the maths back to the real situation, is something I used to skip over. Now I see it as one of the most important steps. The calculation is just the middle part. Understanding the problem and interpreting the answer, those are the parts that really matter.
Okay, now for me, the biggest lesson is about the connection between a small decision and a big impact. We start with one ambulance driver making one decision, but the maths show us that this decision affect not just the patient, but the whole route around the ambulance. Calculus gave us a way to see that connection, and that changed the way I think about what mathematics is for. It's not just about solving problems, it's about understanding how decision ripple outward into the world.
Ah, I think this project also show us what non-routine problems are really for. They are not designed to test if you can follow steps. They test whether you can think. Can you look at a real situation, figure out the right question to ask, build a model, apply the right maths, and then explain what your answer actually means? That's completely different skill from solving a textbook exercise. And it's a skill useful in the real world.
Working on this as a group also make a real difference. We each notice different things. We ask each other questions that we wouldn't have thought of alone. I think that is an important point about maths. It doesn't have to be a solo activity. Talking through a problem with others often helps you understand it better than working alone.
Okay, to wrap up, This project shows us that calculus is more than just a set of rules. It's a way of thinking about change and making better decisions. Whether it's an ambulance trying to save time, or an engineer trying to reduce costs, or anyone trying to make a smart choice in a complicated situation, the ability to model, optimize, and interpret is genuinely useful in the real world. And that's something we will carry with us long after this assignment is submitted.
So, thanks for watching our discussion. We hope it gives you clear picture how we approach this problem. Not just that what we calculate, but how we talk about it. And thank you to our lecturer, Sir Sabri, for giving us problem that make us actually think.
Thank you.
Thank you.
That's all for me. Bye.
Bye.